Every generation or so, a technology comes along that does not just improve on what came before, but fundamentally changes the rules. The printing press did not just make copying manuscripts faster, it restructured how knowledge moved through society. The steam engine did not just speed up travel, it rewired entire economies and made the Industrial Revolution possible. The transistor did not just make radios smaller, it laid the foundation for every digital device that exists today. These were not incremental improvements, they were paradigm shifts, technologies that, once they arrived, made the world before them look unrecognizable in hindsight. So when serious scientists, government agencies, and technology leaders describe quantum computing as potentially the most important technology of the 21st century, that is an extraordinary claim. And extraordinary claims deserve careful, honest examination. Today, that is exactly what we are going to do. Let us start with what quantum computing actually is, briefly, for anyone who is newer to the topic. A quantum computer is a machine that uses the principles of quantum mechanics: superposition, entanglement, and interference to process information in a fundamentally different way from any classical computer. Where a classical computer processes information as bits that are always either 0 or 1, a quantum computer uses qubits that can exist in combinations of 0 and 1 simultaneously. This allows quantum computers to explore vast computational spaces in ways that classical machines cannot efficiently replicate, at least for certain categories of problems. The key phrase there is certain categories of problems. And we will come back to that, because it is one of the most important qualifiers in this entire conversation. The case for quantum computing being transformatively important rests on several pillars, and it is worth examining each of them honestly. The first is drug discovery and medicine. One of the most promising near-term applications of quantum computing is the simulation of molecular and chemical systems. The behavior of molecules is governed by quantum mechanics, which means that simulating it accurately on a classical computer becomes exponentially harder as the molecule gets larger. Even relatively simple molecules push classical simulation to its limits. A sufficiently powerful quantum computer could simulate molecular interactions with a level of accuracy that is completely out of reach today, potentially transforming how we discover new medicines, design new materials, and understand biological processes at the most fundamental level. This is not speculative hand-waving. It is grounded in well-understood quantum chemistry, and it is one of the applications that researchers are most genuinely optimistic about. The second pillar is optimization. An enormous number of real-world problems are, at their core, optimization problems. How do you route thousands of delivery vehicles most efficiently? How do you manage the flow of electricity across a power grid? How do you allocate financial resources to minimize risk and maximize return? How do you design a supply chain that can absorb disruptions? Classical computers can solve these problems, but often only approximately, and at great computational cost. Quantum algorithms, particularly in the medium to long-term future, may be able to find better solutions faster for certain classes of these problems. The degree of advantage, and for which specific problem types, is still an active area of research, and honesty requires acknowledging that quantum optimization is not a guaranteed revolution. It is a promising direction that needs more theoretical and experimental work. The third pillar is cryptography and security, which we have explored in depth in earlier videos. The short version is this: quantum computers pose a genuine long-term threat to much of today's encryption infrastructure. And they also enable entirely new forms of theoretically unbreakable quantum cryptography. This dual role, as both a threat to existing security and an enabler of new security, makes quantum computing centrally important to national security, financial systems, and digital privacy in a way that few other technologies can claim. The fourth pillar is artificial intelligence and machine learning. This is perhaps the most contested area of quantum computing's potential. There is genuine theoretical work exploring how quantum algorithms might accelerate certain machine learning tasks, sampling from complex probability distributions, linear algebra operations, and optimization of neural network training. But it is also an area where the hype has frequently outrun the evidence. Many proposed quantum machine learning speed-ups come with significant caveats. They require data to be in a specific quantum format that is itself difficult to achieve. And recent theoretical work has shown that classical algorithms can close the gap more than initially expected for many proposed quantum ML applications. This is a field where optimism should be tempered with rigor. Now, here is the honest counterpoint that any serious treatment of this question has to include. The title of this video asks whether quantum computing is the most important technology of the 21st century. And the truthful answer right now, in the present moment, is that we do not know. Not because the potential is not real, it is, but because the distance between that potential and its realization remains enormous. The quantum computers that exist today are impressive scientific instruments, but they are not solving practical problems that classical computers cannot also solve. We are in what researchers call the NISQ era, noisy intermediate scale quantum, a phase characterized by machines that are real and operational, but too error-prone and limited in qubit count to demonstrate clear practical advantage on real-world tasks. Building a large-scale, fault-tolerant quantum computer, the kind that could actually deliver on the most transformative promises, is a challenge that may take another decade or two or more. Nobody knows the precise timeline, and history is full of examples of technologies that seemed transformative in theory and took far longer than expected to reach their potential in practice. There is also a question worth sitting with honestly. What else might compete for the title of most important technology of the 21st century? Artificial intelligence, particularly large language models and foundation models, has already demonstrated practical, world-altering impact at a scale and speed that quantum computing has not yet approached. Biotechnology and gene editing, particularly CRISPR, are already reshaping medicine and agriculture. Renewable energy technology is actively reshaping the global energy economy. Any one of these could plausibly claim the title, and the honest position is that the 21st century still has about 75 years left to run. What can be said with genuine confidence is this: quantum computing addresses problems at a level of fundamental importance. The simulation of nature, the security of information, the optimization of complex systems, that places it in a category of technologies with civilizational stakes. The governments of the United States, China, the European Union, the United Kingdom, and many others have collectively committed tens of billions of dollars to quantum research, precisely because they believe those stakes are real. The scientific community has produced Nobel Prize-winning experimental work confirming the physical foundations. The engineering progress over the past decade has been remarkable and continues to accelerate. Whether quantum computing ends up being the defining technology of this century or one of several transformative technologies that reshape it together, its importance is not in serious doubt. The question mark in the title of this video is not false modesty. It is the most honest thing about it.